Hi everyone, my name is Kirsty Anderson and I'm the Principal Manager of Public Engagement for the Global CCS Institute, and I'm going to be your host for this morning's webinar. So welcome to all the people who've tuned in from around the globe in different time zones, and for those of you die-hard enthusiasts that are dialing in your pyjamas from the Americas, the good news is that if you nod off during the webinar, you have a backup. The session is being recorded and will be made available on our website in the near future, so you can listen again or pass it on to your friends or colleagues. Right, today I have the great pleasure of being joined by the co-authors of the report, A Geological Assessment of CO2 Storage in the Baltic Sea region. The full report is on our website now, and you'll see the direct link in one of the slides in this presentation. So I wanted to start by giving a very warm welcome to Richard Vernon and Nick O'Neill, who are poised by their computer at their office in Fair Dublin, ready to give us all a taste of what to expect in the report and, of course, to answer I want to give a very introduction to the project that this report has come from, and that's the SLR 2 project. So you can see from the multitude of logos on this slide that Swedish industry has been a real driving force behind the BASINS are going to be a persistent challenge in future. And in order to evaluate the best options for dealing with this challenge, there's a need to know the relevant conditions for CCS in the Baltic Sea region. So you'll see that an interesting spread of industries have joined forces with the Swedish Energy Agency and the Global CCS Institute to set up a multidisciplinary research project. And the industry represents and minerals. Work Package 1, the geological assessment of the Baltic Sea region, is the slice of pie that I would normally hold out for. March this year, and you'll see the direct link to the report just here at the bottom of this slide. The complete project will have taken just over 2 years to finish all of the individual work packages and deliver a final summary report towards the end of September this year. And then over the summer, or for those of you in the southern hemisphere, the winter, you'll have the opportunity of hearing from Peter Stigson, 2 stores in the Baltic Sea region. Okay, now that we've got our trailers for forthcoming attractions out of the way, let me just introduce you to our presenters. So this is Richard Vernon, and I'm the Technical Director at SLR Consulting. SLR is headquartered in the UK and employs over 1,000 staff worldwide with offices in the UK, South Africa, Namibia, Ireland, Australia, Canada and the USA. Richard and Nick are both based in SLR's CCS practice in Dublin in Ireland. SLR is currently engaged in a wide range of CCS activities, including providing geological, engineering and strategic consultancy to governments, to research institutes, national and international agencies, regulators, power generators and owners of offshore infrastructure that is approaching decommissioning. SLR has 2 representatives on the CCS expert panel of the European Federation of Geologists and is also an approved technical supplier to the International Energy Agency's Greenhouse Gas Research and Development Programme. And here's Nick. This is Nick O'Neill, who is also a director at SLR Consulting. And Nick's background is as a senior manager in the international energy sector, a trained petroleum geologist in exploration and drilling with 25 years experience of strategic energy exploration and management in Europe, the Middle East, Africa, South America and the North Sea. He's responsible within SLR Ireland for generating new business in the energy sector, and Nick is currently project manager for the Irish Petroleum Infrastructure Programme, where he works closely with colleagues in Canada, the USA and Europe. He was the Irish government appointee to the European Seafloor Observatory Network, and in 1994 he established an exploration consultancy business, then joined SLR in 1995 to develop their oil and gas sector. Nick's current research interests include CO2 sequestration, offshore gas hydrates and geothermal potential across Europe and Africa. And Nick has contributed to a number of strategic reports on energy policy, including strategic gas storage, wind energy and CCS. Nick also has an even thicker accent than me, so I can guarantee by the end of this hour webinar you'll all be craving either a shot of whiskey or a pint of Guinness. Right, final housekeeping rules. So we welcome questions throughout the presentations, and I'm going to be moderating those questions as they come in, and I'm going to read out as many as I can at the end of the presentations. So to submit your questions, you just go to the Questions tab on the GoToWebinar control panel on your screen, which should look like the image that you can see that my mouse is highlighting over here. So please feel free to send questions throughout the presentation in preparation for the Q&A session at the end. It's much better if we have an interactive session and you've got the opportunity with Richard and Nick here to get direct answers to all your questions about the Baltic Sea. Okay, without any further ado, I'm going to hand over to Richard, who will take us through his presentation.
Thank you, Kirsty, for that very good introduction, which I think has placed the whole project in a very good perspective. I'm not sure about the Guinness at this time in the morning, but we'll worry about that in a few hours' time. Nick and I are very pleased to be able to present this webinar, and as you can see, the title of our report is Prospective Sites for the Geological Storage of CO2 in the southern Baltic Sea. And what we're going to do is our methodology of storage capacity calculation, talk a bit about the static modeling we undertook, the dynamic modeling that was going to provide a summary and conclusions. I'm going to do the general introduction and the summary and conclusions, and Nick, who's a clever one, will do all the geology and the technical part. We hope to finish this in about half an hour to leave plenty of time for questions. So I think it's important to put this study into perspective, the context. As everybody will be aware, the Baltic states in general and Finland and Sweden in particular are large emitters of CO2. If CCS takes off as a bridging mechanism to fill that gap in technology between where we are now and a clean world, which is needed for global warming, to reduce CO2 emissions for global warming mechanism, the captured CO2 will need to be stored somewhere in geological formations. Based on the current knowledge for the Baltic Sea area, this is probably likely to be in the North Sea, either in Norway or in the UK sector. And as you'll see from the slide here, this will require the captured CO2 to be moved out by a ship. And this will incur a major transportation penalty. So this study is looking at the possibility of storing CO2 in the Baltic Sea in general, and the southern portion of the Swedish sector in particular, to see if that opportunity would enable us to not incur that transportation penalty. There were a number of criteria that were given to us, or we agreed at the beginning of the study. A lot of these are in line with the Carbon Sequestration Leadership Forum guidelines, which that CO2 needs to be stored under 800 meters of a solid cap. And in this case, we needed to identify areas in the Cambrian Sandstone, and that would either be in depleted oil and gas fields or saline aquifers. Our first job, of course, was to accumulate all the data that was available, and we were in a very lucky position because we had a number of sources that had not been available to anyone else trying to do this work before. We started off, of course, with all the general public information from a regional and a country perspective. And then the main asset that we had was the database provided to us by Svenska Petroleum, or otherwise known as OPAP. They had been undertaking oil and gas exploration in the Swedish sector of the Baltic Sea. They had undertaken 32,000 kilometers of 2D seismic, and they drilled 17 wells. And all that data was made available to us for the purpose of the study on a confidential basis. So we had access to the raw data, which we could use in our model, but of course that is very confidential and sensitive and commercial information, so that data is not available, but the output of that data when put into the model has helped us come up with our answers. We also have incorporated a significant amount of data from Kaliningrad, which was made available to us as a result of a visit to St. Petersburg. And we have got information from Poland, the Polish Geological Institute, again, which is not publicly available, which has gone into the study. And we've incorporated data from Latvia and Lithuania, where we've been able to find it. So the result of that, effectively, was a regional map of the sedimentary basins of the Baltic Sea, which you can see here. And basically it shows, if we're going to the small part, there's a little grey part in the middle there, or middle on the left, which is the Dolder structure. The wider orange line is the Dolder's monocline, and the red line around the whole area is the Cambrian, top of the Cambrian at 900 meters. We actually use 900 rather than 800 to be a little bit conservative. So this was the output of the static model, and I'm going to hand over to Nick now, who will go through some of the work we did to establish the storage capacity and the methodology and the results. So Nick, would you like to carry on?
Thanks, Richard. I'm not really the so clever one, but I do have a good team of clever people around me. The basins that Richard has identified were ranked. And I think there's a slight delay on slides coming up, but you should see the ranking of Baltic Sea subbasins for CO2 storage on the screen now. So these basins were ranked according to a methodology by Baku that he developed in 2003. And in this initial ranking, the Uppsala zone, the border zone, has the highest priority, mainly because it contains structures and also contains the Dolder's monocline, which is the one which is most accessible to the Baltic Sea states. The Gdansk-Kura depression is also geologically suitable for CO2 storage. It has existing oil production infrastructure in two places, at Petrobaltic's B3 field and Lukoil's fields both onshore and offshore. And the other two basins, sub-basins, are also ranked, but we concentrated on the top two basins. Following the ranking of the sub-basins, storage capacity calculations were completed using the geocapacity methodology. And you can see the figures here for the regional Cambrian, and within that the Dolder's monocline. And the different methodologies used included the generic hydrocarbon fields methodology, which uses formation volume factors and ultimate recoverable reserves where limited data is available. We also used the detailed hydrocarbon field methodology, where we had some better reservoir and formation data from wireline logs and core. And then there was the saline aquifer storage capacity estimates using regional bulk volume estimates according to Baku formula, and also we approached it from the trapped volume estimate evaluating the storage capacity by looking at actual map closures. We looked at those figures and calculated the amount of storage that is onshore, and you can see from this table the breakdown, and the overall percentage of CO2 storage capacity onshore is 56%. We also looked at the distribution of storage capacity in defined structures by country, and you can see the breakdown in this particular slide. And you'll also notice that Latvia has most of the storage potential. But we have to say that in terms of the definition of the storage, it lies on the boundary between theoretical and effective capacity, as shown on this slide, the CSLF 2007 resource pyramid. So the data that we have is such that we can say that the figures we quote are just within the effective capacity layer within this pyramid. Then, having put together the data in map form, a static model was developed. We looked at the highest ranked basins, and we looked at the structures which had the best potential to provide commercial CO2 storage, and we ranked 4 structures for static modeling. So the 4 areas of interest are shown here: the Dalders structure, the Dalders monocline, the E6 structure and the E7 structure in the offshore Latvian zone. These were selected for static modeling, and once you have an example here of the E7 structure static model, which was it shows the middle Cambrian interval. Out of the static model, we produced a number of outputs, including these maps shown here, which indicate the distribution of porosity and permeability on the Dalders monocline. There's also a seal integrity study. The seal integrity study investigated basic overburden properties above the Middle Cambrian Reservoir. We looked at the stratigraphy, the lithology, and the thickness, as well as the nature of any faulting and fracturing observed in the 2 candidate structures for CO2 storage. So we did have some petrophysical properties for individual stratigraphic units based on wireline logs, and also on some core samples. And these are summarized here in the seal integrity table, which indicates that the Silurian and the Ordovician have good sealing properties. Based on the petrophysical data and the maps of sealing formations, we assessed the caprock integrity. And 3 possible modes of seal failure were identified: top seal failure, migration upbounding fault planes, and leakage across fault planes. And as you can see from this slide, potential for top seal failure is considered to be low. Seal failure resulting in leakage across fault planes, down-throwing Ordovician carbonate lithologies is more likely. But the risk of this is still low. The risk of any leakage is low because the thickness of the reservoir and large throws along the faults well, they reduce the risk of leakage along those faults. We also looked at evidence from analogous fields in the offshore Polish sector, where some small-scale cross-cutting faults were identified, and these are likely to be open. We also looked at the completion of wells where data was available to assess the risk of leakage via poor cement or corrosion. Most wells were completed in an adequate fashion with cement plugs installed. So one would consider that the well completions were adequate, but however, the issue of corrosion is something that would have to be considered if CO2 storage was going to occur in areas where there were existing wells. Static model, the Dalders monocline and the Dalders structure were selected for dynamic modeling. And this dynamic modeling was carried out by the University of Uppsala Earth Science Department. And the specific objectives of the model were to define the reservoir pressure behavior with respect to seal integrity for different injection scenarios based on the petrophysical reservoir properties and hydrogeological aquifer parameters that we established in the static model. Secondly, to calculate the CO2 plume migration tip speed and distance and the potential for dissolution trapping. And three, identify suitable multi-well injection scenarios in the Dalders monocline to meet the estimated industrial CO2 storage requirements identified around the Baltic Sea. And you can see from this slide the reservoir pressure behavior. The preliminary and indicative dynamic modeling for this area suggests that with 5 injection wells, a total injection capacity of 2.5 million tons per annum could be achieved. And reducing the injection period to say 25 years and increasing the number of wells could increase the total injection rate somewhat above this level. So it's possible that including Dalders structure, this area could be suitable as a storage site for CO2 captured from a limited number of industrial facilities. A second multi-well injection simulation using an injection rate of 1 million tons per year in each well was carried out using the vertical equilibrium model. And the results of that modeling is shown here. And you can see the overpressure ratio was one of the parameters we wanted to look at. And you'll see in A above the overpressure ratios after 20 years and after 50 years. And in B below, you can see the plume, let me see, in B, we have the mobile CO2 plume migration with the multiple well injection rate after 50 years and after 500 years. So these were attempts to pick locations for multi-well injection and to model how the overpressure would dissipate, and also to check how the CO2 plume would migrate. So in the next slide you can see an example from the TUF2 simulation showing overpressure build up over 50 years of injection. And this type of modeling the locations for multi-well injections. For instance, in this case, you can see in the lower plot or map that the pressure build-up is very high, and it's important that areas where high overpressure has been modeled would be avoided for well locations. So these simulations can show the pressure interference between the wells and allow us to make site selections and allow us to define the number of wells that can be drilled for injection. The simulation also looked at the CO2 plume spreading, and you can see from this graph. And at this point, I'm going to hand back to Richard.
Okay, thanks, Nick. What I'm going to do now quickly is summarize the overall report, the conclusions and recommendations and way forward. I think the good news is there is a very large theoretical storage capacity available in the Baltic Sea. And we showed you some numbers which are very large, 16 gigatons, which is clearly a very large number. But as we discussed, this is theoretical capacity. We are happy that the sandstones can contain it. We're happy that the cap rock is a good seal. It also goes to say that any injection rate is a function of porosity and permeability. And the areas that we have looked at in detail are relatively poor in terms of its porosity and permeability capability. And therefore, the ability to store very large amounts of CO2 is actually quite limited. So the area that we modeled would be suitable for the storage of industrial-sized operations, say 2.5, 3, 4 million tons a year, but probably would not be suitable for a very large regional storage project, maybe 25, 50 million tons a year. What our studies have shown is that the permeability and porosity improve as you move towards the northeast, up towards Latvia and Kaliningrad. So what we will need to be doing in terms of principal conclusions is to focus more on the regional capacity to store CO2 if we are looking for a regional solution to captured CO2. And the principal recommendations, again, are not that surprising, but they really fall into two areas. There is still a lot of data that is out there, some of which we have as a result of what we talked about earlier on, the work in Kaliningrad, Poland, and the Swedish sector from OPAP. And there is a lot more data, a lot more work that could be done to reduce uncertainties simply by tying together existing data with the general information we have. So there is a lot more potential for further work based on existing data. But obviously, if we are going to do more detailed studies up in the northeast of the monocline, which including Latvia and Kaliningrad, we will need more data. That data we think is available, but it will require further efforts to obtain more of it. Perhaps the most important thing is the need to drill wells. Now, the wells generally are drilled for oil and gas exploration purposes, and what we are recommending strongly is that any wells that are drilled in any area, any country offshore, that engagement is made between the CCS people and the oil and gas companies so that maybe a little bit of extra effort, work, money could be done to the exploration well that would be of great value in the CCS context. So for instance, if an exploration well is unsuccessful for oil and gas, it would be really important that the maximum amount of information was obtained from that unsuccessful oil and gas well, which could be of value to the CCS projects. And we talked about reservoir data from onshore and offshore Latvia and Kaliningrad. And I think the finest, or the most important conclusion from the whole report and from all the work that we have done is, in order to understand better the potential to store CCS, captured CO2 in the Baltic region, it will require an order of magnitude of cooperation between the Baltic states far greater than is the case at the moment. I think great progress has been made. We have incorporated and made contacts with a number of the countries around the Baltic Sea, which were not originally part of the project, but that process needs to be continued in much more depth and rigorousness. So I think those are the principal conclusions and recommendations. And maybe Kirsty, I'll hand back to you now, and then you can see if there's any questions or any debate or discussion, which we will be happy to meet.
Great, thanks Richard. Okay, let me just put my screen up here. So we've had a couple of questions coming through, and let me just start with the first one. I think it's probably going to be Nick to answer this one. The question is there any way to improve our understanding of the porosity and permeability distribution in the Middle Cambrian Reservoir?
Well, yes, as Richard said, we always, us geologists, we're always looking for more data, so more data would help. But even based on the data that we do have, the wireline data and seismic data, we could carry out a more detailed evaluation of the environment of deposition of the Middle Cambrian, so we could get an understanding of where the sweet spots might be for geological storage of CO2. We could use we have good data from, well, let's say there is good data for Kaliningrad, which we haven't actually accessed all of it. There's also good data for the Baltic, the Petro-Baltic field offshore Poland, and if we could use that data to put together analogues and do maybe some stochastic modeling along with the environmental or the environment of deposition. So the combination of all three, analog data, stochastic modeling with an environment of deposition model, we could actually help to identify where the sweet spots are.
Okay, thanks Nick. We've had another question come through. It came through when you were looking at the multi-well function scenarios, and it was just asking, is that scale of injection capacity, so the 2.5 million tonnes per annum that you were discussing, is it significant enough to be interesting to develop for the region? The comment was that it seems small compared to what you would expect the emissions to be. Richard, I think
that's a very good question, and it was really summarised
in your conclusion.
I did, I think, discuss it a little bit. What we have said there is that would be suitable for small say one power plant, one cement plant, something like that. What it is not suitable for, based on the information we have at the moment and the modelling we've done at the moment, what it is not suitable for is a regional project capturing maybe 25 or 50 million tonnes a year. And that's why we recommend further work to the northeast or where we believe the porosity and permeability has better characteristics suitable for CO2 storage.
And this is up near the Latvian borders, is the area you're talking about in the northeast.
Latvia, Kaliningrad.
And if I could just throw in there also, I mean that 2.5, it's restricted by the porosity and permeability characteristics that we have at the moment. But it may be that there are sweet spots, you know, we know now that the Latvian area is better, but there may be sweet spots elsewhere where injection rates, a much higher injection rate would be possible, and that we could have commercial scale injection.
We're talking about in the southern sector here.
Yes.
And how would we go about trying to identify what work would need to be done additionally to identify those?
This environment of deposition study with analogs. Yes.
Yeah.
Okay, thanks guys. I have a couple of fairly technical questions for you, so bear with me. This one asked, how did you rate the potential candidate? You mentioned that you used Baku's method for rating. Could you please elaborate a bit on the method that you used for the rating?
Yes, I mean the rating involved both soft factors and hard factors. So it included criterion such as you know, the size and depth of the storage areas, the hydrogeology, the things such as the geothermal gradient, but also factors such as accessibility in terms of distance, but also in terms of regulation. Like for instance, the Kaliningrad area at present, both onshore and offshore, would not be available for regulatory reasons because EU countries are not allowed to transport CO2 across frontiers. But there's a mixture of geological factors, seismicity, reservoir seal pairs, faulting and fracturing, pressure regime, the presence of fields, hydrocarbon fields, etc., mixed in with regulatory status.
Great. Thanks, Nick. Actually, the similar questions just come through from the same listener, so I'll just finish this one off. They've asked about, again, this capacity of 2.5 million tonnes per year is presumably per well, and they were asking if it's possible to drill more wells to therefore have a higher injection rate. I'm assuming that would just become an economy of scale thing as opposed to...
Kirsty, no. The capacity per well is about 500,000 tonnes per well, and what we had modelled with 5 wells to come up to 2.5 million.
That's great. Thanks for the clarification.
The economics, obviously, of drilling wells that can only store 500,000 tonnes a year does raise a whole number of questions.
Yeah. Okay. We have a question about the Devonian reservoir potential. They've asked, why did the study not look at the Devonian reservoir potential, as it looks like it would be better in comparison to the Dalders monocline?
My recollection was that the depth of the Devonian, we considered the limited amount of data that was available indicated that the porosity and permeability characteristics of the Devonian at that depth would not be appropriate, would be very low.
Okay, thank you. We've also had a question about whether you considered any EOR or enhanced hydrocarbon opportunities.
To a certain extent, we discussed with Lotus their strategy for the offshore field near Gdansk, and they do have a plan to capture CO2 from the Gdansk refinery, and injected into the B3 field. And I'm not sure whether that involved an enhanced oil recovery aspect, and I suspect it does. But that's the only area where it would have been appropriate.
Again, it's worth remembering there are only 2 countries around the Baltic Sea that have offshore production, and that is Poland and Kaliningrad. So if one is talking about EOR offshore, you are limited to those 2 countries at the moment. And obviously we have some data which has been very useful from Kaliningrad and could probably get more, but we have not got into detailed discussions with the operator there. And in Poland, as Nick says, there is a project already in hand which may result in EOR from CO2 captured from the Gdansk refinery.
Okay, a question. Well completion and integrity. You mentioned in one of your earlier slides that this was an area.
Yes, this is always a thorny issue. It is possible to look at the data for well completions, and we certainly did that where the data was available. You can look at the well completion diagrams and see where the cement plugs were put. You can also check the quality of the cement bond logs that were acquired when the cement when casings were cemented and when the plugs at abandonment were set. But there's always the issue that wells drilled in the 1970s, what is the current condition? Is there any corrosion of casing, and has there been any deterioration of the cement bonds? So all we would say is that there should be a health warning that while one can check historical records and verify that wells were properly abandoned or not, one needs to be careful, and if one plans to store CO2 in an area where there are existing abandoned wells, there may be a need to investigate if there are any, is there any potential leakage from those existing wells.
One could also add, of course, that the well could have been abandoned perfectly satisfactory and fit for purpose and still be in the same condition now for the situation that occurred when it was abandoned. But obviously if you are going to inject CO2 and raise the pressure in that area, that needs to be looked at as well. So you're actually changing the conditions by injecting CO2 from what was in effect when they abandoned it, and that adds another complexity of the fit for purpose for a different purpose, if you see what I mean.
So either way, the wells are going to have to be worked over if they're going to be used.
They're going to have to investigate further. And workover, of course, is a technical oil expression, so they will need to be investigated, yes.
Okay, guys, we've had a question through about the selected areas, and they said if candidates selected are aquifer or oil and gas fields, was any consideration to bottom hole pressure increment constraint? Was there any consideration to bottom hole pressure increment constraint, and was it also studied during injectivity calculations?
Well, in relation to that, we had difficulty finding fracture pressure data for the area. So a figure was selected, so 50% above formation pressure was taken as a fracture pressure. So we used that as the constraint in the dynamic modeling. And you will see from the maps produced from the dynamic modeling where we have 50% above formation pressure is the cutoff pressure. So in answer to that question, I think further work needs to be done. We did take account of fractures and bottom hole pressures, but more accurate fracture pressure information is required. That can be obtained from leak-off test data from wells that have been drilled. But that data wasn't immediately available to us.
Okay, we've also had a question through about the areas of study. So I've been asked, why didn't you study the areas southwest of the current study area, so in the direction of Germany or Denmark, and what is the current knowledge about the storage suitability of those areas?
Well, we were the terms of reference were for the Baltic Sea basin. Therefore, our study was confined to that. And to be honest, I'm not aware of the current status for the German basins, but I'm sure the geocapacity report that was produced in 2009 would have information on that.
Okay.
And I think it's worth remembering that a lot of the funding came from Sweden, so our focus initially was the southern portion of the Swedish sector. And given the fact that we had all this data from OPAP, Svenska Petroleum, it made sense to focus on that area where we had good data.
Okay, thanks guys. I've got a question about pressure increases. So we've asked what sort of pressure increases were your models predicting, and is it presented as percentage increases?
50%.
Yeah, as I mentioned earlier, cut-off pressure, in other words, a pressure at which we would have expected a formation to fracture.
Okay, I'm not sure,
So
Tom, you can come back if that's answering your question. The last question I have at the moment, although they are popping in thick and fast, is if there are any scenarios studied, like a case where you produce, which you produce during injection, so you could minimise the pressure increment.
Talking about letting the aquifer, the water out, the open aquifer.
That could be one. Yes, well, everything was modelled as open. I mean, one scenario to release pressure is to drill a relief well, which allows the saline aquifer to produce water and reduce the pressure. In the static model and the dynamic modeling that Uppsala can do now allows us to carry out various scenarios, and therefore, select a sweet spot and inject at different rates with different numbers of wells. So it is possible with the models that we have now to run a number of scenarios.
Great. Sorry, I did say that was the last question, but we have one more. This one is on seal integrity. So I think for you, Nick, it's asking, when you were discussing seal integrity, you mentioned smaller scale cross-cutting structures were likely to be open and that they needed to be considered as the pathways for upward migration. And we're just asking if that was particularly pronounced in any particular area that you studied.
Yes, the identification of those faults came from a survey that was carried out over the B3 field offshore Gdansk by Lotus. In fact, I think it might have been carried out as part of the sidecar project. It certainly indicated multi-beam data acquired by the Gdansk Marine Institute indicated that there were gas chimneys and gas bubbles in the water column, and also pockmarked structures identified from multi-beam on the seabed, and they seemed to be associated with north-south cross-cutting faults. So not the major faults that are responsible for the B3 structure, but later cross-cutting faults. And there are indications that they may be leaking.
Okay. Sorry, just one last question, I promise, and then I'm going to let you go. Just on the CSLF model that you presented fairly early on, you talked about effective capacity, and that you were at the different stages that you were looking at this capacity, and we were just wondering what you would need to do to move your knowledge and your understanding of this area to the practical capacity level in that graphic.
Very simple answer. Drill wells. Drill wells. You can't move up to the top of the pyramid without having well data in that absolute area.
And this is not something that you can get from the oil and gas industry, or you would need to drill your wells for your own purposes?
No, I mean if the oil and gas industry drills the wells in that area, that's fine, and if you have data from it. But you have to have well control and well knowledge in order to move up that pyramid.
Okay.
And that was, if you remember, one of the principal conclusions and recommendations is that where the oil and gas industry was drilling exploration wells, there needs to be discussion between the CCS community and the operator of that well, so as to ensure that even if that well is unsuccessful, as much information that is of use for CCS is obtained as possible.
And Richard, just on that, is there specific, what are the kind of key things that you would be looking for from that well information if you were able to access information from these pure exploration wells?
It's basically all the standard oil industry, which is coring, wireline logs, testing, formation pressure, bottom hole pressure. Nick, more?
Yeah, fracture pressures. Yeah, good well data is what's required. I mean, when you go above we've got the theoretical and we've got the effective, which is sort of based on exploration data. When you get up into the next part of the pyramid, you're actually talking about a reservoir which is suitable. You're starting to match your storage requirements with a specific site, and it has to be suitable not just on the geological grounds but on other grounds also, on accessibility and regulation and those sorts of issues.
I don't know if you guys are going to be able to answer this question or not, but we've had a question come through on that topic just asking what is the projected total cost before there is sufficient certainty for storage to begin after you've been drilling all these wells?
That wasn't really in the terms of reference. And secondly, I don't think there is anything like enough data and information to be able to answer that question. I mean, there's going to be a series of stages that you go through, each one building on the previous one. I don't think one can answer. I could answer that question then.
No, I think it's site-specific to every area where you have a lot of geological information already. The development will depend on what your dynamic modeling indicates, how many wells you're going to need. So it's like looking at the development plan for an oil or gas field. It's very site-specific.
Okay.
And no oil company would come forward with a development plan until it was very certain of the geological conditions in the area where they're proposing to develop, and we're not at that stage yet in the Baltic Sea.
Okay, guys, I was going to call it quits, but we've had one last question. We do have 2 minutes left, so if you don't mind, I'll ask this. The last one that I've had through is from Graham Proud, and he's asked, can the principle of fracking to liberate gas from shale be applied to CCS? So fracking to create storage capacity. I think it's probably quite important to answer that question.
Well, it's I would consider it not really appropriate for CO2 storage. It's a different scenario than one would use for shale gas, where you're trying to get gas out of impermeable formations. In this case, we're trying to get CO2 into really low permeable formations. And I think on the scale that we need, if you look at shale gas, it produces at very low rates for very long periods of time. For CO2, we need to inject large volumes of CO2 over a short period of time. So I don't believe that fracking will help us in this case.
Thanks very much, Nick. Okay, well guys, you've done a power of work answering our questions, and we really appreciate the time and the presentation. I think it's been really informative this morning, so thank you both very much. I also just want to give a quick thanks to Kylie, who's our tech genius that's at the Institute in Australia, who's been working late tonight to keep the webinar running smoothly. And finally, of course, thank you to all of you for joining us and participating in the discussion this afternoon. It's been great. Those questions have been coming through thick and fast, so thank you very much. If we've not answered any of your questions, then please do send us an email through. We can try and get the questions that you were looking for answered. Also, if you have any feedback on the presentations in today's webinar, then please send that feedback through. You can see the address at the bottom of the screen there to send it to. So that's all from us. Thank you, everyone. Good night for those in the Southern Hemisphere, and have a good day to everyone else.